All right, hello everyone. Welcome to today's OpenHW TV episode. As we've done with past episodes, we pre-record some of the content to make the viewing experience better. And we'll start that live stream recording up momentarily. Today's episode is the continuous integration and continuous development environments that we have for our various projects within the OpenHW Group. And I'm joined by a series of panelists. All of the panelists are watching the live stream together with you here today. And we'll play the video and then come back live at the end. It's about 35 minutes of content, and then come back live at the end for Q&A. So I'll get all the panelists to say hello and wave out to everyone. Welcome to you. Thank you very much for being here. And to the attendees, queue up your questions in the Q&A chat window. We'll let them queue up through the course of the live stream of recorded content, and then we'll have an interactive session at the end with all the Q&A. So please sit back, enjoy the video, and we'll be back live in about 35 minutes. Hello, everyone. And welcome to episode 5 of OpenHW TV. In today's episode, we're going to cover the various continuous integration and delivery projects that we have in place, namely around our verification test bench, core-v-verif, and the CORE-V MCU that we're taping out second half of this calendar year. And our speakers today for these projects are Aimee Sutton from Metrics and Tim Saxe from QuickLogic, alongside Mike Thompson and Florian Zaruba from the staff here at the OpenHW Group. Before we get into the content of today's session, I'll provide a quick overview of the OpenHW Group and how we're structured. So the OpenHW Group is an international nonprofit ecosystem registered in Canada, where hardware and software designers can collaborate on open source hardware IP, such as the CORE-V family of open source RISC-V cores. We have an international footprint with developers around the world. And the focus is really on creating high quality hardware IP that can be used in high volume production SoCs in line with industry best practices for how these IP blocks are verified. We have very, very strong support across industry and academia with 64 plus members and partners. And as you can see here on the industry side, we have very large corporations across the industry, from systems vendors, silicon vendors, tools vendors, and software vendors, big companies and small companies, really quite a healthy representation of the overall ecosystem for hardware development. And then on the academic front, many leading institutions that have global recognition for the research work that they do, and a number of very strong partners that help us curate and deliver the open source artifacts that we are working on within the ecosystem. The way that we're structured is a series of task groups that are part of 2 working groups that report into the board of directors. So there's a technical working group and a marketing working group. The technical working group is effectively the engineering department, if you will, of the organization, with a series of task groups that govern the various projects underway. There's a cores task group for the RTL behind the cores themselves, a verification task group doing the verification work, and you'll hear more about that in this episode, a hardware task group, and a software task group. And the software task group works on the tool chains and operating systems that run on the cores. And the hardware task group develops FPGA and SoC implementations, as well as eval platforms and development kits that developers can use to program and evaluate these platforms. And we also have a marketing working group that looks after a number of marketing initiatives, including our university outreach task group. So in today's episode, we're going to cover the verification infrastructure, and in particular, the continuous integration environment and regressions that we run in that infrastructure. And Aimee and Mike will join us shortly for that. Following which, we're going to cover the continuous integration and delivery environments that we've got in place for the CORE-V MCU, which is shown here. And this is a device that we'll be taping out in the second half of this year, built in 22FDX with global foundries, that will include the 32-bit core, the CV E4, alongside an embedded FPGA array from QuickLogic. And we'll build somewhere between 1,000 and 10,000 of these as development kits to put in the hands of software developers. So with that, I'm going to change gears and bring in Aimee and Mike to talk about the verification infrastructure environment that we have, and in particular, how we manage multiple projects within this environment and the continuous integration and regression flows that we have in support of that. Mike, Aimee, over to you guys.
Hey, thanks, Rick. Happy to be back on OpenHW TV. Topics of this presentation, it really is a single topic. I'm going to reintroduce the core-v-verif project. We've talked about this in OpenHW TV before, so I'll make the introduction brief. We're going to talk a lot about our open source, highly distributed workflow. This is really the problem statement that we're trying to solve. And how we're addressing that is with cloud-based continuous integration. And my colleague, Aimee Sutton, will be going into the specifics about that. So what is core-v-verif? At the end of the day, it's a GitHub repository. This is where the verification environment is, the test benches, the test programs, the scriptware for all of our core-v family of cores. So the cores themselves aren't there, but the verification environment for all of them is in the core-v-verif GitHub repository. It's a very active project. On any given month, we'll get about 30 pull requests. We've got 25 to 30 contributors each month. New contributors are always welcome, and I'll show you how we work together. This slide is intended to basically show, really that we are working on multiple projects at the same time. These are the cores that are in active development here at the OpenHW Group. We've got our 6-stage application class cores, multiple variants of 4-stage embedded cores, and coming up later this year, a 2-stage embedded class core. All of these will be either are or will be verified within the core-v-verif GitHub project. Just a little bit about the structural how-to of this. I get a lot of questions about this. How we have one verification environment that can verify multiple different kinds of cores, and how do we do that? Well, the real trick is that we have, for each core, we have a core-specific test bench. We literally call it that, the core test bench. The role of this core test bench is to abstract away the core-specific features that the UVM environment doesn't need to know about. So the UVM environment doesn't need to know about the memory interfaces. A generic core has a memory interface that executes a program. You can abstract that away. And that's how we can have a single UVM environment dealing with multiple cores that may have all physical different interfaces. What I want to talk about mostly today, though, is how we keep this all together from a people working together point of view. And once again, as I've said before, we stand on the shoulders of the giants that came before us. And this is the software development teams that develop workflows for open source software development. We're leveraging that for open source hardware development. We specifically work using a workflow developed by the Eclipse Foundation. Within that workflow, there are two roles that are important. One is a contributor, which can be anybody. A contributor is somebody who contributes source code, and committers. Committers are people who are responsible for reviewing pull requests and approving pull requests and merging code onto one of the active branches or onto the master branch. It's important to know that committers started out their life as contributors. They were elected to the role by the community of contributors of the OpenHW Group. So let's just walk through this a little bit and see how this goes. This is a slide that I've shown in various forms before. Once again, the center of our universe is the GitHub repository. And the GitHub repository is overseen by the committers, and there will almost always be more than one on a given project. The committers are responsible for moving the project forward and And they do that two ways. One is they will create new tasks and assign these to specific contributors, or they will just create a new task and issue as a GitHub issue, and a contributor will pick it up and start working on it. Contributors work in their own environment using their own, either their own tooling or their own compute, or their company's tooling and compute. And they'll work away on the task. And this could be writing a test case, developing a UVM agent, all the usual stuff. They work on that until they're satisfied that it works, and they push it from their user fork onto a development branch on the GitHub repository. This automatically kicks off a metrics CI regression on the Google Cloud, and my colleague Aimee Sutton will be speaking about that in just a little bit. The results of this regression can be seen by anybody, and the committers will certainly see this. And if it passes the regression, the level of the regression that it needs to pass, and if it passes the review, then that code is merged into the development branch or the release branch. And the project moves forward until we've achieved our goals. Talked a little bit about branching, and once again, we're leveraging what's come before us in the software community. Of course, every GitHub repository will have a main or a master branch. What we have in CORE-V MCU is for each individual project, we'll have a release branch and we'll have a developer branch. The release branch is the most stable branch for a given project. This branch has been subjected to a very extensive regression suite, and is, you can rely on that for something. There are some features that are known to be complete in a release branch. Developer branches are a little bit different. Developer branches are a lot more active, and this is where the user commits will come from into the development branch. Development branches are also exposed to a CI regression, but the number of tests in the CI regression is a lot lower, and this allows for quicker turnaround time. So the development branch is stable, but not guaranteed to pass a full-up regression. A release branch will pass that full-up regression, and nothing makes it onto the master branch unless it's complete at some level. Okay, and with that, I will pass things off to my colleague, Aimee Sutton at Metrics, who's going to talk about the details of how this CI workflow actually goes.
Thank you very much, Mike. I'm going to start my presentation by explaining a bit more of the motivation for the creation of this workflow, essentially summarizing some of the points that Mike made earlier. So as Mike explained in his presentation, CORE-V MCU is a single Git repository containing a verification environment that is used by multiple cores. Development is ongoing or will be starting soon for 4 different cores and maybe more coming soon. Development work on CORE-V MCU is separated into multiple long-lived branches. You would have seen those branches in the previous slide. There are dev and release branches for each core and the master branch. And this is a challenge because unlike feature branches, these branches are going to persist throughout the duration of each project, and they're going to be subject to merges from all directions, from different sources and different contributors. Some of these cores are stable, others are highly in flux, but in all cases, code changes which are initially isolated need to be qualified before they are promoted and shared. So how do you qualify these code changes when they're coming in fast and furiously, 4 different cores from different contributors? Well, there is the review process that Mike explained, where committers will manually review the code changes that are made in the form of pull requests. This is a great process, but it could certainly use some help. And that's where continuous integration, or CI, comes in. What is continuous integration? So simply stated, it means that code changes must pass 1 or more regression suites before they are accepted. The simplest example of this is that a pull request or a merge commit made to one of the development branches of CORE-V MCU needs to pass a sanity regression before it is accepted. So the act of running this regression is achieved using a combination of GitHub actions and tools provided by Metrics. Actions are a facility provided by GitHub. They enable users to define workflows that are triggered by events. Workflows are specified using YAML files, and they're highly configurable. So a more complex CI example is a case where the master branch is being updated and several regression suites are launched in parallel. Events that can trigger actions include pushes and pull requests, and in each case, these events can be highly customized. So where do these sanity regressions run? And that's where Metrics comes in. Metrics is a member of the OpenHW Group, and we are a vendor of a SaaS platform for EDA development focused currently on regressions. What does a SaaS platform for EDA development mean? It means simply that you bring your source code and we take care of the rest. We have a system Verilog simulator that's fully compliant with the IEEE standard. We provide hardware orchestration in the cloud, meaning that we bring up virtual machines to run each simulation job in parallel, and we deprovision those machines when they're no longer required. We also have a set of web-based tools, including verification management and artifact viewers for log files, waves, and coverage. So with Metrics, you never need to install any software. Everything is available in the cloud. We also have a REST API, meaning that anything you can do with our web application, you can also do through API. And that is the facility that enables us to work with GitHub Actions. It also enables many other automations. So next, I'm going to show you a diagram illustrating the continuous integration workflow that we've been talking about. And that starts with the committer or contributor. They're doing their work on a fork of core-v verif. They make a push or a pull request to GitHub, and that triggers an action that we've defined. That action launches one or more regressions on the Metrics platform via the API. And as these regressions complete, the results are sent back to GitHub, also using the API. If any test has failed in any regression, the GitHub workflow will fail and the user will be notified. If all regressions pass, then the workflow also succeeds. In all cases, the results are available on the website openhwgroup.metrics.ca, and they're available for anyone who's an OpenHW Group member to access. And with that, I'm going to show you a quick demo of this workflow. So the demo starts here in the core-v verif Git repository on GitHub. And what you see here is the most recent commit was the merge of a pull request. And you see a nice green check mark here. What that green check mark indicates is that the actions or workflows defined to run against this branch have succeeded. So let me click on the green check mark to show you more details. And what that shows you is that all checks have passed. So 4 successful and 4 were skipped. So let's look at the details of one of these checks. And that opens the Actions tab in GitHub. And it shows you all the different actions that were available and the 2 that were run against this particular branch. And then you can see a transcript of the work that was actually being done. So the setup job and the checkout jobs are defined by GitHub in order to obtain the source code needed for this action. So it takes care of checking out the current revision. And then the next stage is the metrics regression, which is defined, user-defined. If I expand this tab, you can see that the status of the regression is reported below. So 38 tests were run, 38 passed, and 0 failed. There's also a summary of coverage results, and then a link to view the full results in the metrics web application. And then finally, a statement saying that all tests have passed, exit with code 0, and that's what causes the nice green check mark to indicate that the action has succeeded and this code should be safe to merge. Let me switch over to the metrics application so you can see what information is available to OpenHW Group members. So here are some detailed information about that regression that was run. You can see the status. It says it's complete, the duration. There were 38 tests and all tests have passed. Some information about coverage, and then links to download artifacts, such as log files. Let me click on the 38 tests that passed, because in the case that something had failed, you might want to view some of the artifacts of this associated with this test, and you can do so right from your web browser. So the green check mark indicates that all these tests have passed, but in the case that something had failed, you could use this link to view the log file, and that log file will open in a separate tab in your browser. The log file opens at the end. If you scroll up just a little bit here, you can see the nice words passed. But in the case of a failure, this would be the first place that you would probably come to look for the reason, the source of the failure. In case a user wants to do a little bit more debug, they have the ability to rerun this regression right from the browser and choose to rerun it using a debug command. So that could be a command that dumps waveforms, but it's user-defined and can provide any other options, such as increasing verbosity or outputting more debug information into separate files. And there's also an option to run only the tests that have failed. In this case, all tests have passed, so the option is grayed out. And then you can click run, and that regression will be launched. In case you'd like to view historical results about this regression, those are also available in metrics. So by scrolling down, you can see the name of the regression and you can click view. And what that brings you is charts showing the performance of this regression historically over time. You can see some points in time where everything failed. 0 tests have passed. So that probably indicates a compile failure. You can also see trends in functional and assertion coverage. And although those might not be that interesting for CI, if you see a sudden dip, it might indicate that something has changed in your code base that's not being picked up by a test failure. Each point on the graph is the link to a separate historical result, and you can always use those for comparison. And the last thing I'm going to show you is that metrics always captures critical information about each regression we run, including the commit and the branch that the regression was run against. And you can use these links to return to GitHub and to view this particular commit. Thank you for your attention during the demo and during my segment of today's presentation. I'll be happy to answer your questions at the end of the session. And for the moment, I'm going to turn it back over to Mike for some closing remarks.
Okay, thanks, Aimee. I've seen that demo a few times, and every time I see it, it gives me joy because it really is something that enables core-v verif to hold together. A question I get a lot is this way of working practical? And the short answer is yes. We've got an existence proof. The CV32E40P used this process to achieve RTL freeze in December of last year. And we're using this exact same process to manage multiple concurrent core verification projects today. Lots going on in open hardware, and I hope you'll come and join us and be part of this new revolution in open source hardware development. Thank you very much, and back to you, Rick.
Thank you, Mike and Aimee. Please stay with us for the Q&A at the end of the session. And as a reminder to all of our attendees, if you have questions along the way, please enter them in the chat box, and we'll get to those questions at the end of the episode. Now I'm going to hand it off to Florian and Tim to talk about the continuous integration and delivery environments that we have in place with the CORE-V MCU. Florian, Tim, welcome to the episode.
Thanks, Rick, for the introduction. And I'm here today to present to you how we embrace continuous integration and continuous delivery in the CORE-V MCU project. But before we get started, let's briefly recap what CI and CD actually is. And continuous integration is really to ensure the integrity of the repository in an automatic fashion. So without any manual intervening, we want to have an automatic way to check the incoming pull request contributions from the different contributors. So imagine this the following scenario. A couple of contributors, they want to contribute code, documentation, and really anything to a given repository. And we are looking at the CORE-V MCU repository in that case. When they open a pull request towards this repository, this automatically triggers a couple of automatic checks. And those automatic checks are described within the repository itself and are very specific to the device under test and to the content of the repository. The automatic checks then come up with either a fail or a pass. In case of a pass, there is also the option that this produces so-called artifacts. So that would be, in our case, bit streams of FPGA tools or any other artifacts like binaries. And then in the last step, an elected committer, and this committer is being elected by a standardized Eclipse-based process, goes and sees, okay, this test failed, this test passed, can communicate what needs to be changed. And then once everybody is happy, and especially the committer is happy, can commit this into the database itself and make this the main master. So why do we want continuous integration for open hardware? Especially for open hardware, we have different companies. We have over 50 different companies in the pot with different backgrounds. We have software companies, toolchain companies, we have hardware companies, and we want to ensure continued quality. And so a saying I really like is that everything that you do not check automatically will eventually break, because there is no way that in a complex project you can always ensure that there is no breaking. And so you really need to check that automatically. This is really a well-known path in software, but hardware is really a bit more new to this and more of a challenge because of the complexity and closed-sourceness of the different tools involved. So why do we want continuous delivery for open hardware? So the same really holds true for continuous delivery. We do have engineers with vastly different amounts of backgrounds. We do have hardware engineers that want to download pre-compiled compilers with IDEs or other embedded software. And on the other side, we have software engineers that want to use pre-compiled bit streams because they want to test their compiler, or they want to run the IDE or the embedded software. And this pre-built binaries really makes it easy to get you off the ground and get you started by downloading pre-built artifacts. So what kind of things do we want to check? So on the one hand, we have style linting. So style linting is really meant to embrace a consistent style across the different open hardware repositories so that every committer, every contributor and committer feels at home with the different styles. We do use variable for style linting of system verilog, Clang format for C and C++ files, as well as Flake 8 for Python. Then we want to automatically have pass and fail criterion on FPGA builds. So we want to ensure that our RTL, our system, continuously builds with the up-to-date FPGA tool chain. And from that pass fail, in case of a pass, we also want to use the pre-built bit streams and upload them to a storage opportunity. And then on the third point, we do have ASIC tools. So we want to embrace the full set of cadence tools and make sure that they continuously work with the RTL that we produce and the changes we propose. So here we are also looking for a pass-fail criterion. And something I want to especially highlight here is the check for sequential equivalence. Imagine that we achieve for a given core RTL freeze. So as we have done with the CV32 E40. And to maintain this RTL freeze without running all the regression tests again and checking the RTL all the time with very large sets of tests, it is important to maintain equivalence in terms of RTL for the given enabled feature set that has been frozen. And so that is really the gatekeeping criterion to accept on RTL frozen repositories new changes. How do we want to run those commercial tools? The tools themselves, they should be packaged in a container. And container is a lightweight virtualization technology, different to virtual machines, that allow us to package the entire file system in the container itself. And that really means is that we can set up a container once, and we can run it on any infrastructure and are very flexible to move between infrastructure, whether it's GitHub or AWS. The container itself is hosted in a private container registry, such as, for example, Amazon ECR or GitHub Container Registry. And then when the pull request comes along and triggers a build, the runner itself that was triggered goes and pulls the container image of the given tool we want to check from this private container registry, runs the check based on the scripts that we have checked into the repository, so that it's really reproducible for everybody, and gives us a pass or fail and uploads artifacts. What do we want to deliver? So on the one hand, as I mentioned, we want to deliver bit streams, FPGA bit streams, and those should also happen on nightly builds, so that we can have most up-to-date bitstream builds. We always have a clear set of regression tests that we can run on those bitstreams, and we make it very easy to get people started with a reasonably new set of features that we have in the CORE-V MCU, and can get them off the ground very easily. We also want to deliver IDE builds, so that it's very easy to just download an IDE, start it up, and hook it up to the also pre-built bitstream on an FPGA. And then finally, we also want to deliver compiler builds, and that is actually, we are already doing this as part of one of our member companies, and because whose page I've copied on this slide deck, they have this very nice page of toolchain downloads, where they also run nightly toolchains and stable toolchains of different compilers, such as GCC and LLVM, and also specifically built versions for our CORE-V set of cores. And this really makes it very easy to just pull down the binary and get started. In terms of the CORE-V MCU, and Tim in a minute is going to touch more about this, we are embracing FPGA builds. As I said, we push the bit streams to our S3 buckets. We are using Verilator as a lint target, and using Verilator as SoC simulation that allows us for very rapid feedback for the given pull request, as well as looking into style linting using variable. We check that our generated documentation is up to date, and we are also checking that sources such as the YAML source file listings are properly formatted, as well as third-party IPs that are checked into the repository for convenience, are not manually modified, but are pulled in on a given snapshot. There's, of course, I want to briefly present the team that is all behind this, so that it's split between hardware and software task groups. On the hardware task group, we have you and Tim, who are leading the hardware task group efforts. And on the software side, we have Jeremy and Yunhai. And I am myself the director of both hardware and software task group, really to kind of enforce the synergy between those two task groups. I encourage everybody to get on board and of course also ask the question at the end of the webinar. I'm happy to answer them. The development is happening in the open. Join our channels, join the discussion, join the CORE-V MCU repository. And yeah, with that, I'm handing over to Tim.
All right, thank you, Florian. Every journey in OpenHW Group starts out with the Git repo because it is an open system. So here's the OpenHW Group Git repo. You can see there are various repos in here for verification in the core, and the one I'm particularly interested in is this CORE-V MCU repo. So if we go there, you see a standard GitHub repo, and over on the right here is a link to one of those artifacts that Florian was talking about, the documentation artifact. So I'm just going to jump to that. So you can see that this documents the user manual for the CORE-V MCU, and it has an overview in it. So I'm just going to dive into the overview. The overview right now tells you the peripherals, but it has this block diagram that shows the heart of the CORE-V MCU. Over on the right is the actual core that OpenHW Group has produced and fully verified. And the purpose of the MCU is to let people evaluate and explore and do development using that core. And of course, the core itself is no use without a bunch of peripherals, so you can talk to it. And then as QuickLogic was an eFPGA vendor, we decided to throw an eFPGA in there for hardware acceleration experiments. So you can see over on the left side, a series of peripherals, UARTs, I2C, SPI, camera interface, SDIO interface, And then the kind of things you'd expect in any MCU, the advanced timers and PWMs and things like that. So the purpose of the MCU project is to not only produce an SoC out of this so that people can evaluate the whole MCU and the core in real world systems, but also to deliver, as Florian mentioned, various intermediate artifacts that let development happen prior to having that SoC available. So some of the artifacts we provide are the bit stream for emulation. We also, because the emulation requires an FPGA board, an FPGA board is $1,000. It's not that expensive, but it is a barrier to entry. We're also working on Verilator simulation, which will give you the ability to run software on top of this whole MCU. Of course, you pay a little bit in performance. So the emulation will run at maybe 10 megahertz. The Verilator simulation will probably run in 100 kilohertz kind of range. The actual SoC will run at 400, 500 megahertz kind of range. But with Verilator, we can do the continuous integration we want to do. So we can run software on the Verilator image. So as part of our continuous integration, we plan to run software images on top of the emulation and also to run them on top of Verilator so that we can check that we have all the linkages. You'll notice in the documentation we have core controllers. So like we have the APB interrupt controller. So here's the automatically produced documentation for the register files. So when Florian was talking about different user bases, one user base for this whole core MCU is the software for the guys that are building the HAL, the guys and gals that are building the HAL, and they need to have all of these register definitions. We drive .h files from this, so the whole .h file definition is another output from this. Now, some people want to develop HALs, some people just want to use the HALs. So we're working on a repo that has a free RTOS implementation and maybe some other implementations in there so that you don't have to work on the HAL, you can work on the application that sits on top of the HAL. We're working with the Eclipse Foundation on an IDE, and we're working with Platform IO people, or Platform IO people working with us to deliver another IDE to layer on top of that so that the application people can use that. So all of this is about bringing down the barriers to entry so that people can work on what they want to do, which is build up this whole ecosystem all the way from RTL up to applications running on top of the system and actually running real applications. So one of the ones that we want to run on top of this is TensorFlow Lite, running a visual application that recognizes people. That will be using the MCU for managing the data, the camera interface for getting the data in, and the eFPGA for accelerating all of that. So again, just invite you all to come in and look at this system, to get involved in using it, and to understand the continuous integration and continuous development for your particular purposes. And if you have a purpose that we don't meet, let us know, and we'll investigate delivering that for you. Thank you.
Okay, thanks very much, guys. Now we're going to open it up to Q&A with the audience. All right. To all the attendees, thanks for sitting through the video with us. We've got a few questions that have come in the Q&A tab. Please don't be shy. You've got these experts available to you over, we've got, another 20 minutes or so till the top of the hour. And we'd be very interested in taking your questions. So one of the questions that came in, and I want to break it into two parts, both the our core-v verif environment and the regression environment for the core-v MCU, was, so what do these tests look like? And can contributors add new tests, contribute new tests? So let's start with the core-v verif environment. Mike and Aimee, you can talk about that a little bit, specifically around the cores. So what do the tests look like? And can contributors contribute new tests?
Okay, so I'll jump on that, Rick, and I'll answer the second question first. Can new contributors add tests? And the answer is yes. The population of contributors is really everyone on Earth. We run, there's a term for it, I believe it's a closed repository. We do not accept a pull request from just anybody. You need to be covered by the Eclipse agreement, our contributor agreement. And that's part of the Eclipse process. That's how we ensure that anything that is contributed is in fact an open source artifact and can be attributed back to a proper license. But once that's done, and that's just a paperwork thing, once that's done, anybody can be a contributor. So anybody can write a test case and get the test case added. And eventually any test case that adds to either the code or the functional coverage will eventually get added to a regression suite. And so then you're in. What does a test look like? There's really two in the core-v verif environment, where we're verifying the cores themselves, the RTL models of the cores themselves. Test case can be one of two things. It can be a UVM test case in the UVM sense of the word, or it can be a test program as in a program that runs on the core itself. And these are two completely separate things, and we do that quite deliberately. So a program that runs on the core itself could be something as trivial as Hello World. And yes, we have a test case called Hello World that does what you expect. It can also be the RISC-V compliance test suite. It can be some tests that we've written ourselves. It can be a test that's written by that we use the Google instruction stream generator to generate random instructions. And those are programs that are generated or manually written in C or RISC-V assembly, translated into machine code by the software tool chain, and then loaded onto the core, where the RTL model of the core actually executes those. The UVM test case controls the UVM environment. And the reason we keep that asynchronous is because the UVM environment spends a lot of its time trying to be tricky. It will generate interrupts asynchronously with respect to the program running on the core, and that's something you definitely want to do. It also generates debug requests. It will set up the operation of the memory interfaces to try to stress out the core in different ways. So that is a very long-winded answer as to what a test case looks like. So in one case, we have UVM test cases controlling the UVM environment. And on the other side, we have test programs that control the execution of the core. Hope that answers the question.
Well, he said long-winded. I'm not going to disagree. Aimee, did he leave any room for you to add anything in there that you want to comment on?
I think that was a very thorough answer.
You're too kind.
We love Mike. He's so thorough. Okay, so that's cool. We've got a bunch of test cases, and we run all this stuff. We got a verified core, and now that serves as an input to the core-v MCU team. We've got a verified and frozen RTL core. What do the tests look like at the core-v MCU level, and how do contributors augment those tests? Either one of you, Tim or Florian, you want to take that? You guys unmute?
Sure, I'll take that.
Okay.
The contribution process is the same as Mike mentioned, so it's the same throughout OpenHW Group actually. The tests we have is actually there's very, very many ways you can test. So what we're doing right now is we tend to run programs that operate on the emulation. So you download a program, run the program can go talk to peripherals. You can do the same thing in Verilator. So you can download a program and run it against the peripherals if you have a peripheral model. The other way to do that is loopback. So if more people generate peripheral models, we use more of those, and if they don't, we'll use more loopback. Then you can imagine with Verilator, you could also do the more conventional test benches that just set up, preload the memory, for instance, and run small pieces of code that exercise the system and talk to peripherals. So actually you sort of essentially have the full range of capabilities. So I think the easiest thing right now is download a program and run it and see what happens with that. The advantage of that, by the way, is then that tests a lot of the other artifacts. So it makes sure that the .h files that tell you where the registers are located are in fact correct with respect to the RTL, make sure the compiler is working the way you expected, and all those kind of things. So you get a top to the bottom integration when you do that. Florian, do you have anything to add to that?
I think that that was very thorough. Maybe also adding that the emulation, I mean, obviously the core is more like, it's all digital design, right? The interfaces are quite well covered, but on the FPGA, on the Core-V MCU, we interface with the real world. So that also means that the FPGA kind of allows us to interface with peripherals that we also want on the emulation platform, that we also want to have on the final product on the development board. And so I think this is quite a valuable add to kind of the emulation work that we are doing with the FPGA.
Great. So I'd like to make a couple of comments just on the contributor model and how that works, and our use of GitHub, and the fact that our engineering release methodology is built on top of the Eclipse development framework, the Eclipse development process. And that is that part of the newness of open source hardware development for our industry is confidence, right? Where does stuff come from? How good is it? How can a high volume SoC company go to production with a bunch of RTL that they downloaded off a GitHub repo? So part of that confidence generation is in tracking where the contributions came from, understanding who the contributors are. We authenticate every GitHub user. Their ID gets authenticated against the Eclipse contributor agreement for individuals that Mike mentioned, or the master contributor and committer agreement, which gets signed off as part of your corporation becoming a member of the OpenHW Group, so that we can instill a high degree of confidence that we know where all the contributions have come from. They are, as I said, the users are authenticated with bots or agents that we run on our GitHub repos. If those agreements aren't in place, they're cross-checked against a database. If those agreements aren't in place to cover that user's contribution, the committer for the repo gets flagged. We go and chase down that user and find out if they're part of a member organization or if they're contributing as an individual, make sure they get the appropriate paperwork in place and licensing in place, so that we can create the highest degree of confidence possible of how this IP was curated, where it came from, and that it in fact can be contributed to an open source repository. Not rocket science by any stretch of the imagination. And as Mike said, we're kind of leveraging the learnings from our colleagues in the open source software community and trying to replicate that as best we can and build on those best practices and modify them as needed to satisfy the needs of hardware developers. So that's something that we take pretty seriously. Okay, coming back to another question here. Do we also run unit tests on individual peripherals? And I'll give a quick answer to that, and then I'll let maybe Florian and Mike talk about it, because we've had a lot of discussion about this. So in so much as the peripherals that we're working with, as they would eventually become a supported IP block within the OpenHW ecosystem, we will eventually get to the full unit tests and fully verified RTL. That's not the purpose of the integration that we're doing. We're not trying to produce a fully verified hardened SoC, but what we are trying to produce is a development platform and a development vehicle for people to exercise the cores and write applications around the cores. Clearly, the peripherals have to work. So the actual peripheral verification work is not to the same degree as our core verification work for that reason. But that's something that will probably change over time. Focus is on the cores, enough work with the integrating the peripherals so that we know that the platforms that we build will work. They're not intended to go to production. The CORE-V MCU device is not a production device, but it is a very, very good development and evaluation platform, which is what we're trying to address. Florian or Tim, do you want to bring any further color to that?
I think just underlining what you kind of said is not yet, right? So, so the first kind of project goal we have within the CORE-V MCU is to bring this test vehicle with this very well verified core and a reasonable running system to kind of in lower volume to the market. But nothing is I mean, we're not concluding any further kind of collaboration or project, especially if members want to come on board. That is definitely something where we are actively looking for contributions on the kind of peripheral verification side, as well as on the peripherals themselves, being it, well verified, understood micro DMA engines or peripheral components. So that is something where we definitely want to go. But the first kind of step is what kind of Rick said, is taking this core and bringing it to a device that is reasonably well verified, so that it can be running applications and can interface with the real world.
Tim, do you want to add anything to that?
No, I think that's a good point. I think it's just an open area in the open hardware ecosystem right now, is to get fully verified peripherals. That's a missing piece. Mike did a big search and couldn't find the verification for even basic things. So that's something that we need to work on.
Yeah, and to that point, if somebody wants to contribute to doing unit tests on some of the peripheral IP that we're integrating into the MCU, you would be very welcome into the community to help drive some of that work. Okay, another question that came in around the IDE work that's underway in our software task group. So just to reiterate for folks, and Florian, I'll throw this to you in a second. There's active development around an Eclipse-based IDE for the CORE-V MCU, and being able to recognize the target and bring up the CORE-V MCU in your development environment, as well as the Platform IO-based IDE. And the question is, if the product is in fact the IDE, how are we doing IDE testing, or how can the IDE testing be incorporated into our CI or CD environment? And I'm not sure I understand the next part. Considering that some tool is used to test the IDE. So Florian, do you have any comments about the work that is happening in the software task group around the IDE projects?
Yeah, so actually just want to widen the scope here a little bit. It's not only IDE, it's also compilers. So compilers are being tested. We have smoke tests for compilers. And what the kind of answer to that is that right now we're looking into as the CORE-V MCU is going to be the basis on the emulation platform. As long as we do not have silicon, the FPGA platform will always be the target for such tests. And there's definitely ideas around setting this up automatically. So that would mean kind of have an FPGA that gets nightly bit streams splashed on it, and then running the GCC smoke tests on it, or running the IDE integration tests with it. And there are kind of a couple of test suites with that. And the IDE in real is the debug module that's interfacing with the CORE-V MCU and the core. So so that is the first step. But then the second step is, once we get back the devices, the PCBs with the actual CORE-V, the physical CORE-V MCU on it, then we can also add this to this kind of chain of testing things. And obviously, once we start evolving the CORE-V MCU, FPGA emulation will always be a very interesting target to, in a reasonable time, to actually test this on real silicon.
Right. Thanks, Florian. One of the topics we get a lot, and Mike kind of referenced it and to the attendees, we've got about 5 more minutes left. So if you have any additional questions, pop them into the Q&A tab and we'll get to them. But one of the topics I think that's worth talking about a little further is what Mike brought up at the end of his talk. Is this a practical way of working? Because pretty much every community or company that's engaging in open source hardware development right now, there's a strong faction of folks inside those organizations that have less of an opinion that this will work, and others that have a strong opinion that this is interesting and will work. So let's talk to this distributed workflow, multi-company engineers, geographically dispersed, working in an open development flow hosted on GitHub, and how we get stuff done. Task assignment, issue assignment, new development of artifacts. It's not just about I found a bug and issuing a pull request, or raising an issue that a bug was found. How do we actually outbound execute with these virtual teams? And maybe Mike, we'll start with you. We've got a few minutes left before the top of the hour, and come back to Florian maybe.
Sure, Rick, I can take that. So how we outbound the work is really, it depends on the specific project and the specific task within the project. One of the things that we use, we've said this before, I think everybody on the call has said this, GitHub is the center of our universe. So we use GitHub Actions to capture tasks. And so there will be, I guess the agile term for this is a backlog of tasks sitting as GitHub issues. People can go and check one of those and say, hey, this is something I'd be willing to do. So they start doing it. That's one way. Another way is for one of the contributors to reach out to a member that is actively working on the project at that time and say, hey, when you're done with the current task, this would be a good task to work on next. And assuming they agree, they'll go off and do that. One of the things about open source development is that you don't have a large team of people all working for the same boss that do things because the boss says so. Everybody works together because we have a common goal. So there's an awful lot of discussion to create tasks, define the order of execution tasks, and to get the tasks in the pipeline to be executed.
We've had a couple of other questions come in, and I want to get as many answered as we can before the top of the hour here. So one is related in particular to the metrics platform, and how hard or easy was it to integrate the metrics platform into our flow? And this is not an open source tool, right? Asked and answered in the same question. So yes, it's not an open source tool, but lots of contributions from the metrics team. And I'll let Mike, before Aimee, you can talk about how hard or easy it's been to launch these regressions through GitHub Actions in our environment, and then give it to Aimee.
Sure. A piece of cake is the answer to the question. It was very easy. I've worked at a number of silicon vendors and IP vendors over the years where we spend an enormous amount of time developing our own infrastructure to run regressions. It's difficult. It's a big task. It takes a long time. You usually have to assign a full-time resource to it. With metrics, it's done. And the team at metrics have clearly done this stuff before. Little things like when you open a log file, it opens at the end of the file, because that's where the error report is going to be, right? Just where the simulation ends. You don't need to look through 100,000 lines of log file to get to the end where the action is. The end is right there. Things like that. So one of the great advantages of working with Open Hardware is our partnership with the metrics team. You're right, it is a closed source tool. We're running with UVM environments. You're going to have to buy a proprietary simulator to run our test bench. So no apologies for that. It really does allow for a new team to come together to get running regressions tomorrow.
Yeah, and maybe I'll stop you from needing to provide too much of a commercial, Aimee. Of course, you're going to say it's easy, and it is. And we have a healthy contribution model from a number of companies, both in terms of contributing engineering staff to the projects, obviously money into the open source organization, but also in contributing tools and overall capability and infrastructure. So the metrics simulation environment in the cloud is a contribution from metrics as a member. Cadence is also a part of the open hardware ecosystem, and we have a full suite of Cadence tools that we use. And I don't know if this was mentioned during the core-v verif talk, but the system Verilog UVM test bench, core-v verif system Verilog UVM test bench, actually runs on all 5 of the commercial system Verilog simulators out there, from Cadence, Mentor, Synopsys, I guess I should say Siemens, Synopsys, Metrics, and Aldec. And there are make files to build the environment in whichever system Verilog environment you need to be running in your organization. That brings us just to a minute past the top of the hour. Thanks for staying with us, everyone. Obviously, continue to reach out to us either in the GitHub repos or on our social media channels. Stay tuned for announcements of what the June version of OpenHW TV will be. And in the meantime, wherever you are, I hope you have a good day. Thanks for joining us.
Thanks, everybody.